Hi, my name is Alireza Karduni. I'm in my home during the coronavirus quarantine. It's raining outside and I really want to be out there. But on behalf of my co-authors, Ryan Wesslen, Isaac Cho, and Wenwen Du, I would like to talk to you about our research on Du Bois' rap bar charts. The Paris Exposition of 1900 devoted a building to matters of social economy. The United States section of the building featured an exhibit devoted to the history and present conditions of African Americans. The expo was set up by W.E.B Du Bois. He was an American sociologist, socialist, historian, civil rights activist, author, writer, and editor. Stumbling upon images from his exposition in this book, we realized that he was also a very profound data visualization artist. His visualizations were colorful and beautiful, telling stories through data about various aspects of African Americans' lives in the United States. But often, they were also innovative and new, using charts and graphs in addition to photographs to tell stories about the disparities African Americans faced in the United States at that time. Some of the data sets that Du Bois dealt with included values that were disproportionately larger than the rest. In this chart, which is about the number of African American students taking the various courses of study in schools of Georgia, the number of students taking industrial courses is disproportionately larger than the rest of the course, especially as compared to the smallest value of the course of business. By setting a threshold for numerical access of his bar chart, he would wrap the largest value along the categorical axis, allowing for the smallest values to be more visible. Now let's take a look at another example. This chart shows the number of COVID-19 cases by country by the month of April 2020. The largest value is about 240,000, and that is for the United States. However, since the number of cases in the United States is so much larger than the other countries, it is especially hard to read the value of the smallest bars, such as Argentina, Mexico, and Egypt. Now, if we apply Du Bois' technique and limit the y-axis, for example, 30 to 30,000 and start wrapping bars larger than that value along the categorical axis, we can see that the bars with the smallest values become more readable and visible as the threshold of the y-axis decreases. We can still read the number of largest values by counting the number of wraps, though, from wrap bar charts and multiplying by the threshold of the y-axis. In this case, for the United States, 8 times 30,000, that will give us 240,000. Looking at the tail of the wrap bar chart, we can see that the value is about 1,500 cases larger than that. In this research, we conduct 3 studies to understand how Du Bois' wrap bar charts would benefit users. In study 1, our main goal was to compare standard and wrap bar charts in terms of users' performance. We measured users' performance through 2 tests. Identification accuracy shows us how and whether users were able to accurately identify the largest and smallest values in a bar chart. Ratio estimation accuracy shows us how accurate users were in calculating ratios between largest and smallest bars. Using a web-based application on Mechanical Turk, users would go through one standard bar chart and one wrap bar chart through 2 different data sets randomly assigned to them. This is a view of the bar charts all users saw in our first study. For example, for the dataset of the number of Facebook ads per presidential candidate, users would either go through the task using a wrap bar chart or a standard bar chart. Our hypothesis for this study was that participants will achieve higher accuracy with wrap bar charts in identifying smallest values. Also, we hypothesized that participants will be more accurate with wrap bar charts in estimating ratios involving smallest values. Now, in terms of identification accuracy, after running this study, we found that compared to standard bar charts, for both datasets, users were more accurate using wrap bar charts when identifying smallest values. They were similarly accurate, though, when identifying the largest value of the bars. In terms of ratio estimation accuracy compared to standard bar charts, We found that for both data sets, again, users were more accurate using wrapped bar charts when calculating ratios of largest to smallest values in a data set. So in study 2, we are asking what kind of data sets are particularly suitable to be represented by Du Bois wrapped bar charts. We used 2 measurements to characterize data sets. Normalized entropy tells us how much of all values in categorical data sets are concentrated in only a few categories. Normalized entropy of a data set is a value between 0 and 1. A-spread tells us how much a certain value in a data set is larger than every other value. A-spread is not a bounded value and could be very large. In this example, we can see one category overwhelming every other value in the data set. This characteristic is represented by a low normalized entropy and a high H-spread. On the other hand, in this data set, no value overwhelms other values. We can see that the normalized entropy in this data set is close to 1, and the H-spread is very low. For study 2, we generated 13 data sets with high variability, each with unique characteristics, ranging from low to high entropy and H-spread. Each bar chart in this matrix shows one of the 13 data sets. For example, the highlighted bar chart shows one data set with an H-spread between 3 and 4.5 and entropy between 0.6 and 0.75. For our second study, each user would go through all 13 data sets twice, once through a standard bar chart and once through a wrapped bar chart. The ordering of the 26 trials were randomized. In this video, we can see how users would first select the largest value, the bar with the largest value, then select the bar with the smallest value. Then, in the text box, users would enter their estimation of the ratio. And they would go through this trial over and over again 26 times. Our hypothesis for study 2 were that participants will achieve a higher identification accuracy for the smallest values with wrapped bar charts for datasets with low normalized entropy. Second hypothesis was that participants will achieve a higher identification accuracy for the smallest values with wrapped bar charts for datasets with high H-spread. Participants will have better large to small accuracy, we hypothesized, in estimating ratios between largest and smallest bars with the wrapped bar charts. And finally, we hypothesized that participants will spend more time with wrapped bar charts when estimating largest to smallest bar ratio. This chart shows us how users' performance with wrapped bar charts compared to standard bar charts with different normalized entropy values. As you can see, for entropy values smaller than 0.75, users were more accurate, more than 15% accurate, in identifying smallest values. We can also see that users were slightly more accurate in identifying largest values using standard bar charts. This chart shows us how users' performance with wrapped bar charts compared to standard bar charts with different H-spread values. For H-spread values larger than 1.5, users were between 5 to 17% more accurate in identifying smallest values. We can also see that users were between 2 to 5% more accurate in identifying largest values using standard bar charts. Now in this chart, we can see that from top row to the bottom row, the distance between the log absolute error confidence intervals between standard and wrapped bar charts increase when the normalized entropy values decrease. We can see that for normalized entropy values larger than 0.6, users calculate the ratios between largest and smallest bars more accurately. Now, in this chart, from bottom row to the top row, the distance between the log absolute error confidence intervals between standard and wrapped bar charts increase when H-spread values increase. We can see that for H-spread values larger than 0.3, users calculate the ratios between largest and smallest bars more accurately. Now, in terms of how much time users spend for calculating the ratios, here we can see that users spend more time to calculate these ratios between the largest and smallest values when using wrapped bar charts. Participants on average spend 8 more seconds to compare the ratio task. Now, let's get to study 3, where we try to understand users' experience with wrapped bar charts through a focus group discussion. We held a class and brought a lot of users in to use the wrap bar charts, similar to the study too. And then we asked them questions on how they experienced different aspects of it and how they came to some of the solutions. So one of the themes that came out at the discussions was that most of them understood the purpose of the wrap bar charts. Out of the 24 participants, 21 mentioned they believe wrap bar charts are useful for specific cases when some values in a dataset are disproportionate. So this is a quote from one of the users. Wrap bar charts are useful when there is an obvious disparate effect from one attribute over the others. If the axis scales were calibrated effectively, though, wrap bar charts could more concisely convey differences in orders of magnitude. So the user, even though understood that there's benefits in using this, they had some complaints about it. In terms of usability of wrap bar charts, 16 participants argued that at some point, the task of estimating values of the wrap bar charts can be cumbersome, especially when there are too many wraps. So one of the users said, wrap bar charts is easier if there are only a couple of wraps, but if the number of wraps increases, it gets harder. Another person said, you need to do additional subtractions when the bar is coming downwards. So what does that mean? In some cases, because of the way wrap bar charts work, the tail end of the bars, as you can see in this image, is facing downwards. So it becomes counterintuitive based on the way the y-axis shows the values to calculate the small proportion at the tail end. And this is something that we need to address. So overall, through the 3 studies, we find specific cases in low entropy and high A-spread where users gain accuracy in identifying identification tasks and ratio tasks while using wrap bar charts. We also see that participants have higher time spent on identifying the largest bars. And the mentions of annoyance with too many wraps provide evidence that wrap bar charts might be less pre-attentive than standard linear bar charts. There's a lot of potential improvements to fix some of these issues. Adding a reverse axis for the downward facing bars, adding altering gaps in wrap bar charts in order to make counting easier are some of the solutions that we came up with for the future. There's also another alternation that we can do to this chart. As you can see in this, we can alter the location where the bars wrap in the bottom of the wrap. So it kind of gives a interesting, intriguing visual effect. But we did not go through to make things more simple, we did not test how users read values when the bars do not wrap at full length of the y-axis. So this completes our studies. I know that at this point, everyone would have a lot of questions, but this would be a very good time to say thank you for listening and watching this video. I really wanted to be at the Chi conference to meet all of you. You can check out this research on multiple views. Try out the application through the link provided. Our team has been doing a lot of other cool work. You can check it out at Karduni.com. And if there's any questions, I would be more than happy to answer it. Please contact me through my email provided here.